Okay, last week we talked about how do we use the discrete time to process the continuous time signals. Okay, we want to mimic this part. Okay, and finally we derived that actually when you take the impulse train sampling, okay, you will duplicate your signal. Okay, and then this Fourier transform and the discrete time Fourier transform, they have a relationship. Okay, omega, and then you will change to omega times Ts. So here is the example. All right, then we focus on the sine or cosine signals. So if I sampled the sine or cosine signals, what happens? Here we have an example to see how aliasing is. So let's quickly see this. I want to plot the discrete time Fourier transform. Okay, so first I sample it. If this sampling rate is less than the Nyquist rate, then we have aliasing. Okay, and this 60, okay, and then our sampling rate is 2 pi over 12. Okay, the omega is 12. So here we say that the highest frequency we can see is 6, because if it is more than 6, then we have aliasing. For example, for this one, if I sample it, okay, here is my sample. Well, here is my Fourier transform. Because it is 6, so we have 6 and minus 6, and we have pi. But for the discrete time Fourier transform, what happens? This omega becomes omega times Ts. So there will be from minus pi to pi. Here is minus pi, and here is pi. Remember, for the discrete time Fourier transform, it is periodic, 2 pi. Okay, so they will continue, which means they will continue. How do they continue? Okay, so they will continue here again. So this is, I will say, this will be 2 pi. And then they will do that here again. So that's why. And also here, they'll duplicate. So that's why this one becomes 2 pi. And here is still pi. This is minus pi. Okay. Then how about like 7.5? We can see that why after 6, then we have aliasing. So what is cosine 7.5 if we sample 2 pi over 12? For the Fourier transform, should be 7.5 minus 7.5, right? Then for the discrete time Fourier transform, 7.5 times Ts, it should be 5 over 4 pi and minus 5 over 4 pi. Okay, this one, then it is periodic, 2 pi. So when they do the periodic, with the 2 pi here, okay, this is 2 pi, so our periodic here. And then this one. And that's why you will see this is the aliasing. Similarly for 9t, okay, in frequency, here, it should be 9 and minus 9, and we have a pi. But 9 times ts, it should be 3 over 2 pi. Okay, here is 3 over 2 pi. But actually, when they, again, if you duplicate that at 2 pi, they will fit here and here. So that's why that we see these two. Okay, the dotted line. Remember that they are periodic. Okay, make sure that you can also plot that by yourself, so you will see why we have aliasing. So we have 10.5, 12. You can do it by yourself and check. And why not this? Here we don't have aliasing. Quickly, we can also plot at 3t. So in the beginning, it should be 3. Here, right? Here's 3, minus 3, and 3. So this is 3 minus 3. It's pi, pi. This is in continuous way time. Then for the discrete time Fourier transform, right, we have pi, 2 pi, not 2, it's pi, 2 pi, minus 2 pi. All right, 3 times ts, 3 times ts will be pi over 2. So in beginning, that's your signal here, pi over 2, and also minus pi over 2. Okay, and here is x. And now you duplicate and 2 pi here and here. Right, so they'll put this and here. So when you see the spectrum from minus pi to minus pi to pi, there's no aliasing, like a ghost signals come in. Okay, remember it is periodic. Next week the meeting will be in Mechanical Engineering Building 109. Okay, not this place, not this building, in Mechanical Engineering 109. All right, if you don't have any questions about this one, let's see another example. Okay, my sampling rate, sampling period will be 2 pi over 9, and my signal is this one. So first I need to plot the DTFT of this signal. So to plot the DTFT, first we can plot the Fourier transform of this one. Okay. And then your omega times Ts will be your DTFT. So what is sine t over pi t? This is sine t over pi t will be minus 1, 1. Okay. And sine 3t over pi t here will be minus 3 and 3. Okay? And you times ts. So here's ts, ts. So what is the Fourier transform of the continuous time signal? First, this is the Fourier transform of the continuous time signal. From minus 1 to 1, here plus this. Okay, so from minus 1 to 1, we have 2, otherwise it is 1. So we should have minus 3, minus 2, minus 1, 1, 2, 3. Okay, overall it should be this. So here is Ts. This is 2Ts. What is the bandwidth of this signal? Now let's check the sampling rate. Okay, so omega s. Omega s should be 2t over ts. That's 9. And now 9 is greater than the bandwidth times 2, which is the Nyquist rate. That is 6. So do we have aliasing? There's no aliasing because your sampling rate is greater than the Nyquist rate. So no aliasing. Alright, to plot the DTFT, omega d is omega m ts. Okay, so there will be 3 ts, which is 2 pi over 3. Okay, let's plot it. So the figure should be still the same. Okay, but we will we only plot it from minus pi to pi. Suppose this is pi and this is minus pi. How much? How much? How much? How much? How much is here? Our t is 2 pi over 9, right? So 3 times 2 pi over 9 will be 2 pi over 3. And how about this one? 2 pi over 9. And this is minus 2 pi over 9 and minus 2 pi over 3. Remember that even though we only plot from minus pi to pi, but actually it is periodic. Okay, you can also expect 2 here will be pi over 3. This is pi over 3 minus pi over 3. Oh, and here is 1. Here's 2. Next one, if the sampling period is 2 pi over 6. Now, first we need to check if this frequency sampling rate is greater than the Nyquist rate or not. So, omega s is 6. That is just the Nyquist rate. So your DTFT of your signal will be so it is just right at the Nyquist rate. So here we have pi minus pi. And this is minus pi over 3, pi over 3. Yeah. And then we, because it is periodic, so we expect another shape exactly the same will be here. You can also check like 3 times 2 pi over 6, so there will be pi. Right, minus 3 times 2 pi over 6, there will be minus pi. And then they need to duplicate this signal because it is periodic. All right, next one, 2 pi over 5. What is the sampling rate? Omega s is 5. Now it is less than the Nyquist rate. So we have aliasing. So for the aliasing, how do we plot aliasing? First, we can think about that. If I sample it, okay, in continuous time, then what is xp omega? Okay, for xp, we know that's from minus 3 to 3. So it is from minus 3, here's minus 2, minus 1, 1, 2, 3. Okay, I will sample at 5. So at 5, that means here at 5. At 5, I will copy this to here. So, okay, so 5 is the center. Okay, so the center they'll move to 5 here. So actually it should be around here. And another one, 5 is here. Okay. So we'll overlap this part. Okay. 5 is the center. Minus 5 is the center. Okay. So we got overlap here. So here we have overlap. And then how do we plot the DTFT? So every analog frequency mapped to the digital frequency by multiplying TS, as what we did. Okay, so here we need to times TS, times TS, times TS. So when omega equals 2.5, that means they will map to 5 over 2 times 2 pi over 5, which is pi. Okay, so 2.5, this will map to pi. Omega 1, omega equals 1 will map to 1 times 2 pi over 5. So it'll be 2 pi over 5. And omega equals 2. Okay, that will be 2 times 2 pi over 5. So we get 4 pi over 5. So eventually, the DTFT, you have pi over 5, 2 pi over 5, 3 pi over 5, 4 pi over 5, and pi. Your turn. Please plot it on the screen. I only need to plot from minus pi to pi, right? So from minus pi to pi, and we found that actually when omega is 2.5, it's pi. Okay, so I only need to plot this one and match to here. Okay, so 2.5 here, that is pi, and the value will be 2. So I only have value 1 from here, 1 to 2. So 1 to 2, 1 is 2 pi over 5, 2 is 4 pi over 5. So this part, I have 1, others there will be 2. Therefore, what is the color? Brown. So from 2 pi over 5 to 4 pi over 5, that's 1. Otherwise, it is 2. Because it is periodic, so after pi, there's still 2. Okay, so we'll only cut this one to this one. Let me see. Okay, and then they'll do the periodic. So here, they will connect to here. This is 1, this is 2. Remember that this, we have overlap, so this value actually here is 2 TS. Okay, here I just show you the concept. Okay, they will overlap. All right. Now consider another signal. Okay, I have this signal in imaginary part, and then I sample it 2 pi over 40. I need to plot the DTFT of x1. So for this one, we can rearrange the expression of x1 first. So this means this is TS, times the sinc function times 2j times sine 5t. Okay, 1 pi t that cancel out. So this is Ts times the sinc function e to the I use j 5t, and then minus Ts sine 5t divided by pi t e to the minus j 5t. So sinc function times exponential doing the shift, modulation doing the shift to the right, shift to the left. So the Fourier transform is I have a rectangular pulse, right? But I shift to the right and then shift to the left. So I will get here Ts, and this is 10. Shift to the right by 5, so from 5 to 10. And then shift to the left, but upside down because I have a negative sign. So minus 10, here's minus Ts. What is the bandwidth of this signal? Alright, the bandwidth is not like total, okay, the bandwidth is just here, 10. So the omega is 10, which means my sampling rate should be greater than how much? 20, the Nyquist rate. Okay, so the sampling rate should be greater than 20. But let's see. Actually, the sampling rate here is 40. Okay, so here is 40. So that's greater than 2 times the bandwidth. Okay, which is just 20. So no aliasing. Then your DTFT one over Ts so you times Ts to get your DTFT. So ten times Ts will be pi over 2. So here is pi over 2, and this is minus pi over 2. And then here we have a pi. So here's 2 pi. I will have another one here, another one here. Okay, no aliasing. Let's plot it. Still in this shape. But here is pi over 2. This is minus pi over 2. Here's minus 1, 1, and here is pi, and minus pi, replicate of your signal, because it is periodic, and here as well. Alright, if the sampling period is 2 pi over 15, what is the sampling rate? So if the sampling rate is 15, in this case, do we have aliasing or not? Why? Yeah, because the Nyquist rate is 20. Okay, the sampling rate is 15, but it is less than 20, so we have aliasing. So here, for this example, you can also check when the aliasing starts. So the aliasing starts at omega s minus your bandwidth times Ts, which is 15 minus 10 times 2 pi over 15, which is 2 pi over 3. So it starts at 5, and also that in your DTFT plot, starting at 2 pi over 3. Okay, so how do we plot this? First, we can plot that for the continuous time Fourier transform, because later on we times Ts, then you get your DTFT. So don't think about applying the DTFT immediately, okay? Especially for the aliasing issue, sometimes it's hard to imagine. So first, this is still at 1p. For continuous time. So for continuous time, we find out it starts at 5. So normally it should be 1 to 10, right? So here to 10. So this is 10, and this is 10. So this is 10, 5, minus 5, minus 10. Okay, check this. Why do we have aliasing? Because your sampling rate is 15. So here, when we have 15 here, so everything you'll go. The center is 15. So you, which means that you shift by 15. So when you shift by 15, this 10 will go to 25. And then your 5 go to the right by 15. You get 5 here. Okay, so this part will be here. So you have this will be minus 15. And this is minus 25. This is minus 15, minus 20, and minus 25. Okay, so overall, overall it looks like okay, here's my final answer. Oh, and this is 1 and minus 1. So we have 1 from 0 to 5, and then they cancel out. Right, from 5 to 10, they cancel out. Next, from 10, there'll be minus 1 to 15. And similarly, okay, so here we have 5, 10, 15, 20, and here's minus 5, minus 10, minus 15, and minus 20. And actually, this periodic. So once you have the continuous time Fourier transform, during the break, you can plot then what is the dt of t. Okay, figure out that what is the dt of t. For the dt of t, just times ts. Okay, everything times ts. So you get the brown. So on. So here we have 5 becomes 2 pi over 3. Here's minus 2 pi over 3. And here's pi. Then this is 4 pi over 3. 2 pi. And that's it. Okay. Make sure that you can plot the dt of t in different sampling rate. Like 15 times ts, so why? So that's why we have 2 pi here. Okay, so here will be a minus 2 pi. Yeah, what is the height? The height should be 1. Right. So I think here they got this is ts. Okay. All right, next I have a signal. Okay. Now, first, this signal is the input to a low-pass filter. Okay, and here is the low-pass filter impulse response. Then after, so this is x naught, we have a low-pass filter, and then we get our signal. Okay. So first, we want to so this is a low-pass filter, so I may filter out some signals. Okay, but how do you know which one? So first we need to plot the Fourier transform of the low pass filter. Okay, so again, this one 15 minus 15, 15. Here you have 5, 5. So actually it should be like a step. Okay, and then you times 2j sine. So you shift to the right and shift to the left and reverse. You should get low pass filter. Okay. For 10, 20, 30, 1, 2, so here I have 1, 2, minus 1, minus 2, minus 10, minus 20, minus 30. So after having the Fourier transform or the frequency domain of the low pass filter, so what is X? So this times here. So what do we preserve? This one 232? No. 216? No wonder I feel like why I don't know why there's a 2 here. 32 and 16. I didn't notice that. Okay. But no matter what, they will filter out. Okay. How about 12? 8? 16. We have 16. Wait a minute, let me see. Actually, 4, 8, 12, 16, 32, that's outside. But for 12 and 16, I got 2 times that. Okay, so actually this is e to the j40, e to the j80, and then double the signal at 12 and also 16. I think we should also have 24, right? It should be symmetric. Oh, and then 28. Hey, how come that we missed this too? 12, 16. All right. So 24 and 28. And then we have minus. So minus, minus, this will double, and to here. So minus e to the minus j 40 minus e to the minus j 80 minus 2 e to the minus j 12 and minus 2 this is my final signal. When there's 0, that's 0. It's e to the j 0 t, right? At 0, that's 0. So now this signal is sampled at sampling rate 64. Okay, so now x is sampled at a rate 64, which also means the sample period is 2 pi over 64. Okay, and we can form a discrete signal. So if I sample at 2 pi over 64, my xn is e to the j pi 8n e to the j 2 pi over 8n plus 2 times e to the j 3 pi over 8n, and the fourth term e to the j 4 pi over 8n, and 6 pi over 8n e to the j 7 pi over 8n. Right, this is my discrete signal. And then omega d is omega times Ts. So if you want to see the dt of t of the discrete signal, we have k times 4 2 pi over 64. That's k over pi times pi over 8. So the k is 1 minus 1, 2 minus 2, because we only have this 1, 2, 3, 4, and 6, 7. So suppose this signal is the input. So x is the input to a discrete time, linear time invariant system with impulse response, and the impulse response is h If I have an impulse response like this in their frequency domain, okay, rectangular, doing the convolution, they have the same width, so the trapezoid becomes a triangle. So this will be a triangle. So this will be triangle. The filter. Okay, so here's the purple. Okay, this is a discrete time Fourier transform. So it is periodic. And from this, it should be pi. And here is minus pi. And the height is 8. And now get 6. Four. And 2. Okay, I have, this is 6, 4, and 2. When it is 6, it should be pi over 4. 4, that's pi over 2. And then 3 pi over 4. And you can find the frequency response. Pi over 8 is 7 here. And then 3 pi over 8 is 5. 7 pi over 8 is 1. So the output from here and here. Okay, the output we know 7 times this 5 and also and 6 for pi over 4 and so on. Okay, so let me just write down the answer first. 7 e to the j pi over 8, and we have 6 e to the j pi over 2 pi over 8. And we've got 10. And 8. And 6. And alright, so here's our output. Any questions for this? Alright, next we're going to talk about the modulation. So what is the modulation? So we can change the frequency of a signal. So what is the modulation? The process of embedding an information-bearing signal into another signal. then we need to demodulate that. So here's a demodulation, the process of extracting the information bearing signal. And we will learn what is the multiplexing. We can do something simultaneously. So simultaneously transmission of more than one signal, having the overlapping spectrum. Because we want to save our time and money, it's better like sometimes we transmit a lot of signals, but in different frequency or in other ways. We will learn two ways to do it. So what is the modulation? Remember that when we learn the property of the Fourier transform, right? A signal in time, if you times the complex exponential or cosine or sine, in frequency domain, you shift your frequency. Okay, so this is like a modulation. And why do we need to do it? We will see the reason here. So now let's see what is the general amplitude modulation. I have a signal. The signal is always called like information bearing signal. I times a carrier signal. When I times the carrier signal, then the output is transmitted signal, or we say it is a modulated signal. So if the Fourier transform of the information bearing signal is x, and also the carrier signal, we have Fourier transform, then the output in frequency domain, they times together. So in frequency domain, they are doing the convolution. So here is the convolution. Okay, so the frequency domain of the output is a convolution. Now first, let's see what is the carrier signal. So we have two cases. The first case is the amplitude modulation. With this C, the carrier signal is complex exponential. If it is a complex exponential, we know that the Fourier transform of the complex exponential is an impulse, okay, shift by omega c. It's like here I have a magnitude 1 at times the complex exponential, so I shift in the frequency domain. So this means that my y, because I shift and do the convolution, so the output is just like my input signal shift by omega c. So suppose this is the input in frequency domain, and then this is the exponential complex exponential, but in frequency domain it is a stern an impulse. So when they do the convolution, they just map this to here. Okay, we can also write it down y because y omega, that's 1 over 2 pi we do the convolution in frequency domain, so that is 1 over 2 pi delta function convolved x. So that's why it is a shift of the spectrum of the input signal by omega c. So here you can see that the signal is centered around the carrier frequency. This is a carrier frequency, omega c here, right? So instead of in the baseband, now it's centered at around the carrier frequency. And the modulator may be implemented with the real arithmetic operations. We can using the Euler formula, cosine and J sine. Because here the complex exponential, how do we implement that? Think about the Euler formula. So in this case, my signal, this is a real valued. I can separate into two parts. First I times cosine, and then the second here I times sine. So in the result, this one is the real part of our output, and here it is the imaginary part of our output. We call this this path here is in-phase branch, and then this one is quadrature branch. So overall, this is like a quadrature modulator. And how do we demodulate that? To get my signal back, just the output times the complex conjugate. Complex exponential. And here we have minus sign, so they cancel out that. Because y is x times c, right? So x times c now is exponential, so x times c e to the j omega ct. So you need to times e to the minus j omega ct. So they cancel it. Y equals this. So when you if you times minus j omega ct, so they cancel out, they will get x. So to get your x back, this signal, the output times e to the minus j omega ct. And normally, later on, the other case is that the carrier is cosine rather than the complex exponential, because actually the complex exponential is very expensive. So instead of doing the both, then we just times the cosine part. Alright, so if the carrier is just cosine, then what is the Fourier transform of that? It's pi, and then the shift to the right by omega c, and shift to the left by omega c. Okay, so suppose this is my signal in frequency domain, and I will do the convolution and also the carrier frequency, the carrier here. So I shift to the right and left by omega c, and the magnitude is pi. So when I do the convolution, it's just like my signal shift will move, and or we say like centered around the carrier frequency. And the magnitude go half. And typically the carrier is much greater than your bandwidth. Omega c is much greater than omega m. Right, again, then if you have a signal, then what is the bandwidth? Only omega m, not 2 omega m. Okay. So for this AM, okay, we have to restrict that the signal X is band limit. Okay. If it is not band limit, then we can get the carrier frequency that's higher than the bandwidth. And also because the complex exponential carriers are more expensive, so normally people just use this cosine. But once I modulate that signal, how do we do the demodulation? Because we still want to get my signal back here. So if we modulate, how do we demodulate? Here we have two types, the synchronous and also asynchronous way. But this is a little bit difficult. We won't mention too much in this class. We'll only focus on the synchronous, or we can call the coherent demodulation. The receiver has exact knowledge of a carrier phase and frequency. So we know that when we have this carrier, we know the frequency and the phase. Let's see how do we do the demodulation. So we assume that the carrier frequency is greater than your bandwidth. Okay, and your output is your x times cosine. So if we times cosine again, if we times this again, that means there will be x cosine squared. So cosine squared is this one. If we rearrange the cosine square, in this case, the new signal is half of the original signal plus half of the signal times the cosine. This is like a modulated signal. So W is 1/2 x plus 1/2 x times cosine 2 omega c t. The first one is the scale version. Make it bigger. Of the designed information bearing signal of a desired information bearing signal. The second part and here you see they have 2 omega c. So the second part is a modulated signal. And then the carrier is 2 omega c. So suppose that your output is already this one, right? And the magnitude is 1/2. And this is omega c minus omega m, omega c plus omega m. And you can imagine that why omega c should be greater than, much greater than your bandwidth to avoid any aliasing later. And then here is omega c, and then pi, and pi. Right, this is y, but how about w? W, this signal is like this y, and I times cosine again. So if I times cosine again here, okay, this times this one, not times, it's in frequency domain, that's doing the convolution. So if they do the convolution, this will come here, this will come here, and this will come here again. Okay, so maybe this one. So well, you need to flip. Yeah, flip, they're still the same. So you see, like when they do this here, you get one more, and here. So when you're sliding, finally you'll get here. So when they times cosine, the magnitude will go half. So I have 1/4 and 1/4, but in the middle, because I have 1/4 and here I have 1/4, this one I have a 1/4 and 1/4 here. So finally this is still 1/2 in the center. And then we can select the portion with the ideal low-pass filter. So when we have a low-pass filter, then we can get my signal back. Because y, the output times cosine, again, we got the w. For the w is this one. So if I have a low-pass filter and the magnitude, the height is 2. So 2 times 1/2, there'll be 1. Okay. And in this case, I will get my signal x back. So for those low-pass filter, they will eliminate the double frequency. Here the double frequency means this term, 1/2 cosine 2 omega ct. And for this low-pass filter, how about the frequency of the low-pass filter? Okay, this low-pass filter, the frequency should be between your bandwidth and 2 omega c minus omega m. You cannot choose here, right? In this case, then I have this part. Right, any questions for this? So far, the carrier, we know the carrier, the phase and the frequency, so it is synchronized. So what if it is not synchronized, which means that we have modulator with phase. We use that in the demodulator. So cosine omega ct in modulator is a modulator, but cosine omega ct plus theta in the demodulator. In this case, my w be x cosine omega ct, that is the output, right? The output y times cosine omega ct plus theta. Then we have 1/2 x, we have cosine theta x, and 1/2 x cosine 2 omega ct plus theta. For this part, we can remove this part just like by filtering. Can be removed by filtering, just as before. But for this one, for this part, at the output of low pass filter, and again with 2, we may just get pretty close signal, that is cosine theta xt, instead just the original signal. So we'll have the cosine theta. So what should we do? If it is not just the x, we can use the envelope detection to do it. Okay, you can learn that in the advanced course. We also have the FM frequency modulation, but we won't talk about that here. I know like some teams you are doing this, so we may see that in the final week. Right, next let's see what is the frequency division multiplexing and also time division multiplexing. So what is FDM? When a channel used to transmit a signal has more bandwidth than is needed to carry one typical signal, then we can just transmit several signals together. And then each signal will allocate with a frequency slot. In this case, many signals are transmitted at the same time over a single or wideband channel. Just use a single set of transmission facilities, which means that I can send many signals at the same time. So in that case, in time domain, I may have like sine signal and cosine signal, and some noise or something. So in this case, in time domain, it is really hard to actually distinguish or find out which line, which signal it is. In this case, we can use the frequency division multiplexing. So the signals may mix in time domain, but they can separate in frequency domain. How? Suppose I have a 3 signal. Okay, this signal, their frequency domain here. Signal 2 is triangle. Signal 3, that's a sinc function, so I have a square. Okay, so if I have this 3 signal in time domain, you can see the how mass it is. But now in frequency domain, what should we do? This I can times cosine omega 1 t. This one I times cosine omega 2t. This I have a different omega 3t. In this case, every time we know that when we times the cosine, it's like doing the modulation. So in the frequency domain, I shift your signal. So here, but I shift in different omega, and then add it together and do something later. So in this case, suppose I times omega 1 for signal 1. The output looks like this here. But signal 2, omega 2 is much bigger, so here's omega 2. For omega 3 is bigger, much bigger than omega 1 and 2. When I add them together, you can see we separate those signals. Okay, and then we can use the filter. We use the low pass filter. I can retrieve x1. We can have a band pass filter. I can get x2 or even x3. Okay. So here is a note. To extract one particular signal on one particular carrier, okay, we can use the bandpass filter and then apply the demodulation. So once I use this bandpass filter, I get this. I only have this one. To demodulate, we just times cosine omega again. Okay, they can go back to the baseband. Or we can just multiply. Yes, typo. We can multiply the full received signal by the sinusoidal and also low pass filter. Okay, that is the concept of FDM. Because in time domain, too many signals together, and it's really hard to distinguish each one. So we can let them to the frequency domain with a different carrier, so we can separate those signals. Right. The other one is like, rather than the frequency division, can I do like a time division multiplexing? Okay, just think reverse, like maybe in frequency domain it is in the mass, but in time domain I can get the signal here. So each signal is allocated with a time slot in a period t, and many signals are transmitted at the same time, but the signals are mixed in frequency domain, but it can separate it in time domain. The concept is that maybe here is the signal 1. Okay, I can take this part, I can sample just here, but for x2 I sampled here, and x3 this case. If I can do that carefully, I can reconstruct the signal perfectly, choosing a good carrier and sampling and the sample rate. You may ask, well, maybe can we get this kind of signal like a here, 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 here? No, if they have a good sampling rate, they can distinguish these three. All right. If you are interested about this one, maybe later on you can take like a communication. The communication, this advanced course, or even digital signal processing. Okay. We have two big topics left, which is Laplace transform and also Z transform. Let's talk about the Laplace transform first. So what is a Laplace transform? When we learned LTI system, we know that the complex exponential are eigenfunctions. And whatever we have as our input, the output, same thing, but at times a scalar. But now, if I say S is just j omega, in this case, this is the complex exponential. And still go to LTI system. Here we also have like a coefficient or scaled times the same frequency here. So if the input is a combination of the complex exponentials, then the system behavior will be determined by the h. What is this h? We know h is transfer function. And what is the transfer function? We define that the transfer function is here. The h, the lowercase h, is impulse response. And then if my S, this S is just the imaginary part, j omega, then we get h omega, which is just the Fourier transform. Here we call the frequency response. So you can see that the Fourier transform is a spatial case of the Laplace transform. The Laplace transform at any signal x is here the definition. If you really focus on the frequency, then we use the Fourier transform, because the Fourier transform, it's only talking about the frequency. But overall, this S should be delta sigma plus j omega. I also have a real part. So here is the difference between the Laplace transform and the Fourier transform. For the Fourier transform of a signal is just like the Laplace transform, but we restrict the S be pure imaginary. I think here I should have lowercase of S. So here is the real part and imaginary part. So we only focus on the imaginary part, that is the Fourier transform. We can also obtain Laplace transform from the Fourier transform, because here is the Laplace transform. Okay, for S is the sigma plus j omega. Okay, so if we are plugging sigma plus j omega, we get e to the minus sigma plus j omega t dt. And this is x e to the minus sigma t and e to the minus j omega t dt. So this actually is the Fourier transform of xt e to the minus sigma t. Right, if we think this is the f of x Fourier transform. Okay, so this is the Fourier transform of x times e to the minus sigma t. Alright, let's see some examples and then find out more details about Laplace transform. So first, if the signal is exponential, what is the Laplace transform? So S e to the minus st dt. Okay, so my signal is exponential and the unit step function, and then S is sigma plus j omega t dt. So for the unit step function, I only need to integrate from 0 to infinity, e to the minus alpha plus sigma t and e to the minus j omega t dt. Fourier transform of this one. Okay. The answer is either 1 over alpha plus s or infinity. When alpha plus sigma is greater than 0, then we have value. Otherwise, it is infinity. Here, that also means the region of convergence should be greater than minus alpha. Why? Okay, so from here, let's see. This one, because the integration will get 1 minus e to the minus t alpha plus sigma times e to the minus j omega t divided by alpha plus sigma plus j omega, and t is from 0 to infinity. It will either diverge or converge. So it will diverge. When will we diverge? When alpha plus sigma is less than or equal to 0. it will converge and converge to 0 when alpha plus sigma is greater than 0. Okay, because e to the minus alpha plus st dt, this you'll get what? Minus 1 over alpha plus s e to the minus alpha plus s t. And t is from 0 to infinity. Okay. So here, when t is 0, that's okay, but when t is infinity, then this one should be greater than 0. So overall, this is negative. So here's the real part of S, imaginary part of S. So suppose here, so those areas or region are good. They won't diverge. Alright, another way to find the Laplace transform. We know that for the Laplace transform, actually this is the Fourier transform of your signal times e to the minus sigma t. So we can have the y, that is x times e to the minus sigma t. So x is e to the minus alpha t times ut times e to the minus sigma t. So there will be exponential to the power alpha minus sigma t. And we know e to the minus theta t ut, their Fourier transform is 1 over theta plus j omega for theta is greater than 0. So we can compute the y that's the Fourier transform of your yt. So it will be 1 divided by theta will be sigma plus alpha and then plus j omega. So it is 1 over alpha plus s. And alpha plus delta should be greater than 0. So the delta, the alpha plus sigma, so the sigma, that's the real part of your S, should be greater than minus alpha. Kind of like doing the advanced mathematics. Let's see another example and with some observation. So here you can see now my signal is e to the minus alpha t times the unit step function. Here another exponential times the inverse, the reverse of the unit step function. Okay, I want to find the Laplace transform. Now you can see x of s so we only have values from negative infinity to 0. Okay, because of this unit step function reverse unit step function. And we have e to the minus t alpha plus s and alpha plus s when t is from minus infinity to 0. Then we get what? 1 divided by alpha plus sigma plus j omega. Alpha plus sigma should be less than 0, which means the real part of s is less than minus alpha. And this is still 1 over alpha plus s. You can see that from these two examples, I get the same Laplace transform. Okay, but actually the region is different. Okay, so here are some properties about this, and also what is minus exponential to the minus alpha t. Let's plot here. Alpha is real and alpha is greater than 0. So for Laplace transform, we may get the same result, but actually the region, the area should be different. Here you can see that this is the Fourier transform. Fourier transform, you can see that we focus on the frequency, so only on the imaginary axis. But Laplace transform, well, if we do the Fourier transform, the x, if I times the exponential to the minus sigma 1t, then it's here. Okay, and here there will be x times this sigma 2. In the imaginary axis, okay, these are the bases, so they are orthogonal. Okay, here will be omega 1, omega 2. here omega 1, omega 2, omega 3, they are orthogonal. But are they orthogonal here? I mean, e to the sigma 1 plus j omega 1 t, and also e to the sigma 2 plus j omega 2 t. Remember to download an updated material. Okay. Are they orthogonal? Actually, they are not. So they are not orthogonal. The Laplace transform is just a generalization of the Fourier transform, or the Fourier transform is just a special case of Laplace transform. So the Laplace transform may not be well defined for all S. And why do we need to learn that? Because they may perform more analysis for the signals and systems. And we can cover more signals here. After the midterm, then we will talk about the properties and some fun examples here. Okay.